I mean, the large language models are very impressive. They do have emergent properties. They are surprisingly good at some things. They're also surprisingly bad when they go wrong. If there was anything resembling intelligence at work in those models, they would not make the horrendous errors that they do. Is the brain fundamentally understandable? I think it is. It's complex. Is it modelable? Yes. How big a computer does it need? Well, that depends on how far down you go. There's an important question as to whether we want our machines to be genuinely intelligent or whether we prefer them to stay as useful automata. I think there's quite an important philosophical question there. General intelligence has advantages and disadvantages. An automata will do what its instructions.
Pocket phone.
Sun or rain, an intelligent system may decide it doesn't want to do that, which will make it rather less useful as a production tool.
Thank you for joining Once Changing the World, India's first Future Tech Meets Sustainability podcast. I'm your host, Eddie Avil, and today we have the honor of speaking with a true pioneer and visionary in the world of computer engineering, Professor Steve Furber. He is the ICL Professor of Computer Engineering at the University of Manchester, a Fellow of the Royal Society, the Royal Academy of Engineering, and a Commander of the Order of the British Empire. Many might know him as the principal designer of the BBC Microcomputer and crucially the ARM 32-bit RISC microprocessor, the architecture that now powers billions of devices worldwide from smartphones to embedded systems. More recently, his groundbreaking work has focused on understanding the human brain through computation, leading the SpiNNaker Spiking Neural Network Architecture project, a massively parallel system designed to model parts of the brain. So, Professor, really appreciate you taking time being part of the podcast. You've been part of two groundbreaking products, the BBC Microcomputer for education, ARM 32-bit RISC microprocessor. Currently powers billions of smartphones, tablets, wearables, and IoT devices. It would be great if you could give us a little background, lowdown, what were the challenges, and maybe the key design philosophies that guided your approach to designing these transformative systems.
Okay, thank you for that introduction, Eddie. Well, the story starts a long time ago. Both the development of the first ARM processor and of the BBC Micro were in the early 1980s, so over 40 years ago now. And the BBC Micro grew out of Acorn's interest in the home computer market. Acorn had started as a small microprocessor consultancy and then started building kits for hobbyists to use as home computers. The very early kits had hexadecimal keypads and hexadecimal displays, and you could write code in hexadecimal and run it. But then that developed into something more recognizable today as a computer with a keyboard, usually plugged into a conventional domestic TV screen as a display. And then Acorn became aware of the BBC's interest in effectively sponsoring a microcomputer for a TV series they wanted to produce. They have this remit to educate the general public and decided that the microprocessor revolution was important. And so they invited bids from a number of UK companies. Now, of course, at that time, in the early 80s, microcomputers were a very niche business. We were a long way off today's position where everybody sort of sits at a desk with a computer and has one in their home as well. In those days, computers were large machines in big air-conditioned rooms, tended by people in white coats. So the idea of having a computer that you could use at home or on your desk was very new. The hobbyist market, of course, had taken off in the US in the late 70s. And Acorn bid for this, and because they had a track record in selling the earlier Atom desktop personal computer, they were successful in securing the contract. And I think there were various factors that led to the BBC choosing Acorn as its supplier, one of which was Acorn's apparent ability to develop things very quickly when necessary. I mean, there's this sort of well-recorded week when at the start of the week we had nothing, and the BBC came on Friday and saw a working demonstration of the machine and also a mock-up of the case that it would ultimately go in. So Acorn's very quick to produce things such as prototypes. And the key concept in the BBC Micro was the idea that the memory is the most expensive resource in a home computer. And so this was shared between the processor and the graphics display in a flexible way. And the memory was worked very hard. In those days, running the memory at 4 mega accesses a second was pushing it very hard. And that's what the BBC Micro did. And that gave it a sort of highly integrated and flexible solution. It was also a machine with a lot of I/O ports. So ports for connecting external joysticks and digital analog converters. It had a very early form of networking, which again was relatively unheard of in those days. And it also had an interface where you could add a second processor. So you could add a Z80 running CPM if you wanted to run that kind of software. Again, this was before the early days of DOS and the IBM PC becoming a well-established standard. But you could also, usefully for the Acorn R&D team, you could add second processors from any of the 16-bit microprocessors that were available in subsequent years. And it was also the second processor interface that was used for the early ARM development work. Now, while Acorn was considering what to do to build on the success of the BBC Micro, that we tried out pretty much every 16-bit processor available on the market and found things about them that we didn't like. One of the most notable was that they all had worse real-time response than the 6502 that we'd used in the BBC Micro, which of course was an 8-bit processor. And these 16-bit processors had complex instruction sets to a greater or lesser extent inspired by the mini computers of the late 1970s. And these long, complex instructions had a very negative impact on their real-time response, their ability to, for example, take an interrupt for every byte of data transferred from a floppy disk. And the other feature of those processors that we didn't like was that they couldn't make the best use of memory. I've already said memory was the most expensive component in the system, so not to use it fully seemed to us to be a big mistake. And while we were thinking about these things and considering what processor Acorn might use, and going to 16-bit was the obvious thing, we got news of the papers being published in the west coast of the US on RISC processors, particularly from Berkeley and Stanford, and toyed with the idea of designing our own processor. And that sort of toying became a project, and the project became the ARM chip. Of course, at that stage, ARM stood for Acorn RISC Machine. So RISC was ARM's middle name. Very much inspired by the West Coast work, but with our own take as to what was important in processor instruction set architecture as well. And much to our surprise, after 18 months of development, we had a working processor on our hands that was very low power and very competitive with any of the major industrial offerings at the time. And that processor arrived on the 26th of April, 1985. So just over 40 years ago to the day.
Wow, how cool is that? 40 years of the RISC processor. Professor, what's the evolution been like? Specifically these microcomputers. Because today we are like miniaturizing technology. What once used to be like these large computers, and now gone to like pretty much like small, pocket size. Your phones are like a computer of the sort. So what's the natural evolution going to look like in computers? Because there is this augmented reality, virtual reality, mixed reality technology where they're trying to stack a computer in your glasses. So there is one group of people who are saying that the future of computing is going to be like wearable devices, where it's going to go from carrying technology to wearing technology, your head wearable devices. So maybe my first question is that, well, what's the evolution that you see of computers? And then the RISC processors, what was the vision, and what was the potential applications, and does that compare to its widespread adoption that you see today in smartphones and embedded systems? Did you anticipate that?
Well, I think I'll take the second of those questions first. Predicting the future is very hard, and I don't think I'm any better placed to do that than anybody else. But in terms of what ARM was designed for, it was designed as a processor for Acorn's desktop PC products. That was the business Acorn was in. It had sold a lot of BBC Micros into education, and it wished to build on that. So the first product based around the ARM was the Archimedes. Of course, the ARM was not a single chip. The Archimedes was based on a set of 4 chips, of which the ARM was the processor, and then there was a memory controller, a video controller, and an I/O processor. And those 4 chips, together with memory devices, made up the Archimedes machine. So the objective from 1985 with the first ARM chip until the end of the 80s was really to put processors in Acorn's desktop products to make them competitive with what the rest of the world was doing. And of course, by 85, the world was very much focusing on the IBM PC as the standard architecture. So that was the competition for machines such as the Archimedes. Now, I said this was 40 years ago when this started, and a lot of things have happened since then. Probably the starting point was when, at the end of the 80s, in fact in 1990, I actually left Acorn to move to the ICL chair at Manchester. And just after that, Apple came wanting to talk to Acorn about using the ARM processor in the Apple Newton product. Now, a lot of people today don't remember the Apple Newton, but in the early 90s, it had a very high profile. It was Apple's first attempt at a kind of personal digital assistant product, a sort of handwriting-based system that ultimately was not a success. But for several years, it was a very high-profile development, and Apple talked to Acorn about setting the ARM activity up separately from Acorn as a joint venture involving those 2 computer companies and VLSI Technology, who were a chip fab whose tools Acorn used. So that company was set up in late 1990, and from then on, all the ARM development took place within the company, which was originally called Advanced RISC Machines Limited. So they changed the A from Acorn to Advanced to sort of separate it from Acorn as the holding company. And of course, later they dropped the expansion altogether, and it's now simply known as ARM. But they then looked initially, of course, at supplying the needs of the 2 companies that had formed them. So developing the ARM 610 for the Apple Newton product and continuing to develop processors for Acorn's desktop PC family. But Robin Saxby, who was brought in to lead ARM, was very actively looking for new markets outside those 2 companies in order to allow the company to expand. And the big turning point came in the mid-90s when ARM secured the Nokia business. And Nokia in the 90s, again, many people today don't remember this, but Nokia was the world's largest manufacturer of mobile phone handsets in the 90s. So getting the Nokia business was a very major step for ARM, and led to ARM becoming the standard processor for mobile phones and a lot of similar products, to the point where I understand that the cumulative shipment of ARM-powered chips to date is now over 300 billion.
Yeah.
ARM-powered chips. So
Yeah.
it's an absolutely staggering number, and nobody in the early days in the 80s could possibly have imagined that this was going on. And of course, I mentioned the Apple Newton. One of the differences between the Newton and what followed is that the Newton was not primarily a communicating product. It was primarily a standalone product. And then, of course, 10 years later, 15 years later, Apple brought out the iPhone, which was kind of conceptually similar, but communication was fundamental because, of course, it was a phone. That was its primary function, was a phone, and all the sort of PDA capabilities were built on top of it being a phone, which made it a very different product from the Apple Newton. I'm sure they learned a lot from the Newton that fed into the iPhone, but it was the iPhone that sort of transformed the world of smartphones, and it basically was the start of what we see around us everywhere today.
Professor, any intuit on what the future of computing is going to look like? And you've been particularly push driving the conversation of energy efficient computing. How does that continue to influence your approach to modern processor designing?
Well, yes, energy efficiency was important to the first ARM, but not quite in an obvious way. When we were designing the first ARM chip, what we were aware of was the fact that there were two ways you could package chips to assemble them into computers. One was to put them in a plastic package. Plastic packages were very cheap, but could only handle about a watt of power before they would overheat. And the alternative was ceramic packages, which could handle several watts, but were very expensive. So we were very keen when designing the ARM to keep it within the 1 watt envelope. And of course, the tools available for predicting the power consumption of a chip in those days were not totally reliable. And so we effectively over-engineered the efficiency on the first ARM chip, and it came in at just under 1/10 of a watt. So it was energy efficient from the outset, but not for the obvious reason of going into a mobile system. It was to go into cheap plastic packaging. But energy efficiency has been a sort of hallmark of ARM chips ever since, and obviously was important in going to the mobile phone business, and it's important in many other areas. And it's now advanced to the stage that I have a set of Apple AirPods, and I think each AirPod that you put in your ear contains a quad-core ARM processor. I mean, this is a ridiculous amount of computer power to put in your ear, but of course gives it immense capabilities in terms of noise cancelling and processing sound coming from some radio link device, typically an iPhone. And I think this enables us to integrate significant compute into a lot of different things that we carry around all the time. Now, where that's going to go, I'm not sure. I mean, people talk a lot about glasses with cameras and projecting onto the back of the screen. And that's been tried 2 or 3 times now, and I still don't see a lot of them around. Virtual reality systems, of course, take that even further. You have a complete headset. I can't really see people walking the streets wearing those headsets anytime soon, and even wearing glasses. I mean, I never wore glasses until I got the usual sort of middle-age failure of my near vision. So I've worn glasses since my mid-40s. But I don't think young people will want to wear glasses just because that enables them to have this IT system on their nose. I think they prefer not.
Yeah, Professor, I mean, the future looks so exciting as well as scary. You rightfully pointed out, I mean, nobody would want to wear these intrusive glasses which could pack in your complete computer. It could be a single device where it'll be like a computer and your phone. I mean, the idea sounds cool, but, it's too intrusive. And I guess that's the reason I think Google Glasses failed. And then, there are others who are in the fray trying to kind of build something which is becomes. But I guess technology forever has been in the miniaturizing spree, and it's inevitable that maybe possibly someday maybe we'll be able to possibly pack in something which could be maybe like an ambient device which is non-intrusive, because with the acceleration of AI, I think there's a convergence of sorts with these technologies, and maybe possibly there could be a device which could be maybe on your body, maybe like how Humane tried with this AI pin. Maybe it could be something around that. You've been engaged with the Human Brain Project. It will be great if you could explain what the Human Brain Project is, what was its vision, and why that is shut down.
So, well, the Human Brain Project was an EU-funded flagship project. It started with the first flagship call, and the funding started in 2013. But it was a notional sort of €1 billion budget, so it was a huge project. The central concept was based around the idea that that neuroscience produces huge amounts of scientific results. I think there are the order of 100,000 papers published every year on neuroscience, and nobody can read them all. So there are lots of these little bits of data all over the place that you have to spend a lot of time finding and understanding, and if you want to use it. And so the key idea behind the Human Brain Project was that this data could all be sort of centralized in ICT systems to make it much more accessible and available. And it's important to remember that the Human Brain Project was funded under the EU's ICT program. So it was centrally about using computers in brain science. But it covered a broad area, from medicine at one end, using ICT to integrate data across multiple European hospitals. And this allowed aspects of brain disease to be studied across bigger populations. And of course, larger populations allow you to see things that you can't see with the smaller populations. And that is a very tricky area of ICT because there's lots of personal privacy issues involved. And there were sort of important rules that the data on any individual would never leave the hospital where it was hosted. So you couldn't simply take the data out and put it all in one place. You had to work with it in its distributed form. But even so, it was possible, for example, to identify new types of Alzheimer's by looking at these large data sets. So medicine was one end. Neuroscience, neuroscientific experiments, from wet labs through computational neuroscience to brain modeling, was kind of at the center. And then there was using our partial knowledge of the brain to inform the design of novel computer systems at the other end, which is where we were involved in the neuromorphic technologies. And that ended up effectively as supporting two large-scale neuromorphic computing platforms, one being the SpiNNaker machine at Manchester, which is an all-digital many-core brain-inspired computing system. And the other platform was the BrainScout system at Heidelberg, which was closer to Carver Mead's original concept from the 1980s of neuromorphic technology, using analog circuits to build direct emulations of areas of brain function. And these two systems were set up as openly accessible platforms, so anybody from anywhere in the world could at no cost sign up for an account and submit jobs to these two platforms. And certainly on SpiNNaker we had 400 or 500 users, who ran millions of jobs over the course of the HBP. Now, why did the HBP end? Well, it was a 10-year project and the 10 years came up, right? Like all research funding, it doesn't go on forever.
The Human Brain Project, I mean, the core theme was to kind of, model the brain, and brain, I think it's something that we have very little understanding about, though I think, the world, all over, I think research labs are working towards kind of understanding or unpacking what, our brain does, 80 billion neurons, 100 trillion synapses, the way they fire and wire, how they bring out all of 5 senses is still a mystery, though there are these, various groups of people. There are people working with something called as connectomics, where they are trying to, simulate a C. elegans worm. It's got only 302 neurons, already simulated that. Then there's a fruit worm that we managed to kind of simulate. Then there is Google and Harvard, which managed to kind of simulate a 1 cubic millimeter of a human brain. Blue Brain project by Henry Markram was trying to build in silico brain, but still we are failing. So Stephen Hawking, he compared the brain to a computer. What are your thoughts on that? Is brain similar to a computer? And second question, is it possible to simulate, a brain? And if yes, how far are we from simulating a human brain?
Okay, so there are a lot of questions there. You're right. The brain is a very complex system, and we're still a long way from having a usable, high-level overview of how the brain functions. Okay, we know a great deal about the lower-level details. So we know a lot about neurons and their dynamics. We know quite a lot about synapses and their dynamics. And of course, the brain is not just neurons. There are other cells in the brain that have some kind of role that's less well understood, such as glial cells, astrocytes, and so on. Most brain modeling focuses on the neurons, and the neurons communicate principally by emitting spikes, although some neurons perform other roles, such as emitting neuromodulators. All of these things can be modeled. One particular area of focus during the HBP was on a model of the cortex, a square millimeter of cortex. This was the Potians-Diesmann model that several people worked on, and it became a kind of benchmark for comparing neuromorphic platforms against high-performance computers and GPU simulators and so on. And we know the cortical microcircuit, which neurons connect to which other neurons, how many connections there are, what the overall network structure looks like. We can model it, and the models accurately reproduce biological data such as firing rates in the different layers of the cortex and so on. So we have a fair degree of confidence that these models are capturing something important, but despite the fact that the circuit is relatively straightforward and well understood, and the simulations appear to reproduce biological data quite well, we still don't understand this basic circuit. Okay, and part of the difficulty is if you take any brain region, then it has inputs from other brain regions and outputs to other brain regions. And we don't really understand the inputs or the outputs. If we did understand the inputs and outputs well, then we'd be much better placed to understand the functionality that connects them. But while we don't understand either input or output, it's quite hard to understand functionality. And progress is being made across all of these fronts. The progress in the HBP was really quite impressive. But it's far from complete, and the brain is built of many different regions. The network topologies are quite different. So if you compare, for example, the cerebellum with the cortex, they're quite different structures. The cerebellum is older. It does detailed motor control in ways which are kind of understood to a degree. But its internal circuits are quite different from the cortex. And that's true of many other brain regions as well. So in fact, understanding the brain is not solving one problem. It's solving 1,000 problems, and it will take time. There's also the question as to whether, the standard model, if you like, of neurons sending spikes to each other through networks is actually a sufficiently complete description of the brain, that understanding that model will lead to understanding the brain. There's this debate as to whether there are different physical principles at work in parts of the brain. Now, I think most neuroscientists are skeptical. But of course, Roger Penrose very famously published a book in the 90s called The Emperor's New Mind, which argues that the standard sort of Newtonian neural model of the brain is not sufficient to explain the mysteries of consciousness and human intelligence. Now, as I say, most neuroscientists I've spoken to don't seem to agree with Penrose, but that's quite a complex argument. We won't know the outcome until we've got much further down the road. Is the brain fundamentally understandable? I think it is. It's complex, so it may take a machine to capture all the aspects simultaneously. Is it modelable? Yes. How big a computer does it need? Well, that depends on how far down you go. I mean, a lot of historic modeling has been a sort of one neuron at a time modeling. So you build a neural network with large numbers of neurons, and on SpiNNaker we can model hundreds of millions of neurons running in biological real time. But those are based on a relatively simple model of the neuron. It's known as a point neuron model, where basically the inputs are all sort of come in, multiplied by weights, added, processed, and the output goes out as spike train. But there's growing evidence that the biological neuron is actually computationally much richer than that. That there are nonlinear processes going in on the dendrites. So a neuron is not a single nonlinear process at the center. It may be hundreds of nonlinear processes all connected together through these biological wires in the dendritic structures. And that, of course, increases the computational complexity. It's still computable, but it increases the computational requirement by, who knows, 2-3 orders of magnitude. And estimates of the computational power required to model the human brain at the point neuron level tend to come out at about exascale. And we now just have exascale supercomputers. But if you now add in that dendritic complexity, there's another 3 orders of magnitude of compute power required. So we'll get there, but it may take another 20 years. But of course, having the compute power is a necessary but not sufficient part of being able to build the model. The model requires an awful lot of knowledge as well, and a lot of that is missing.
Here we are, I think, some of the finest, brightest minds in the world trying to kind of figure out a brain and then possibly reverse engineer that into building a, general purpose intelligence, but we still haven't kind of figured that out. Then there is this other group of people, who feel or believe that this data in, data out model, statistical models will bring them towards, general purpose machines. And somehow it's very counterintuitive, but yet these statistical models are showing some emergent properties. So what are your thoughts on these data in, data out large language models, these multimodal models, which have passed, the Turing test and, whatever benchmarks they are there, they're still kind of, passing all of them. Do you think that this current approach of data in, data out model could lead with the scaling hypothesis, where more data, more compute, more power, and algorithm? Could that be the approach to building general purpose intelligent machines?
In parallel with the SpiNNaker project over the last 20 years, there's been this huge progress in industrial AI systems, and speculation as to where the end point of that development will be. My view is that the large language model trajectory is not pointing towards AGI. Large language models basically are just next word predictors. Okay, they have very large data sets. They have infeasibly large parameter sets. So, of course, they're subject to the usual overfitting problems of machine learning systems with too many parameters. And, of course, you say more data, but there is no more data. Effectively, these current large language models are trained on all the data that exists, including arguably some data they should not be trained on because it's copyright. Without appropriate permission and arrangements with the owners of the copyright, there's no way that copyright material should be fed into these models. But it is. And I think there are some interesting court cases coming up on that one. But one of my big concerns about large language models is their dependence on huge data sets. The example I often quote is that the first Google network that got good at recognizing cats was shown about 10 million pictures of cats before it became proficient. And I compare that with a 2-year-old human who will see one cat and then recognize cats reliably for the rest of their lives. Okay, so biological systems can learn very effectively with very small data sets. And that's a huge difference. And some of that is because the biological brain has an aspect of intelligence and ability to generalize that's completely lacking in the large language models. I mean, the large language models are very impressive. They do have emergent properties. They are surprisingly good at some things. They're also surprisingly bad when they go wrong. And that should be telling us something. Okay, that if there was anything resembling intelligence at work in those models, they would not make the horrendous errors that they do.
True. True.
So, and I don't think that will be fixed by bigger models and more data. I think that will be fixed by understanding how biological brains perform intelligence. If you look at the very small brain of something like a fruit fly, about 100,000 neurons, and what it can achieve with that, this is telling you that there's something fundamentally different about how biological brains achieve their objectives and their capabilities. And we need to understand that because the energy costs of large models are just getting completely unsustainable.
Professor, do you see an approach where maybe the Neuro Inspired AI could catch up to these data in, data or out models? Because at this point in time, with whatever said, I think these models, these large language models, are doing things which are quite crazy. So do you see an approach with maybe like the Neuromorphic computer that you're working on could play a catch-up game, and will be great if you could share updates on the SpiNNaker project?
Well, the current state of the SpiNNaker project is within the Human Brain Project, as well as establishing a service on the first SpiNNaker system. We also co-developed a second-generation system with TU Dresden in Germany, and TU Dresden is actively commercializing SpiNNaker 2, as we call the second-generation system, and they are selling large machines. I mean, the SpiNNaker 1 machine has 1 million processors in Manchester. The SpiNNaker 2 machine will have up to 5 million processors. And they are focusing in the early stages at using this for much more energy efficient AI. Now, the early wins there, I think, will be based on translating things like large language models into an appropriate form to run on SpiNNaker 2 hardware. But of course, those translated models, they'll be more efficient, but they'll still suffer from, they'll have the same strengths and weaknesses as the models, the original models that run on GPUs. And we need to learn more about the fundamentals of biological brains in order to really get the advantages that are potentially there. But there will be advantages just from the translation in the early stages. The kind of problems that arise are, just look at the number of people now working on mainstream AI, large language models. I suspect it runs into the hundreds of thousands, whereas people working on equivalent neuromorphic systems, it's closer to the hundreds, right? So there's a very big difference between the amount of human resource that's going into making advances in these two fields. And I think when some of the merits of neuromorphic systems begin to be visible, then I think that balance will start to shift. But it will take some time, and it will take a lot of human energy and resource to really get the best out of neuromorphic platforms.
Right. I really hope that the shift happens, because yes, I think biological intelligence is the true way. I mean, if we are ever to build general purpose intelligence, maybe we need to possibly reverse engineer and mimic biological intelligence, and that could be the way. And I hope that the ecosystem kind of understands that, because I think the general tendency is, when there is something which is in the hype cycle, the industry, the investors, they all run towards that. In also the developers and the engineers. And I think that's the reason I think we're seeing this rush towards building these large language models and being with the blinkers on, just doing one thing. When there is I think the right way to kind of build these general purpose machines would be to reverse engineer like a brain. Maybe possibly start with like a C. elegans worm, a fruit fly, a monkey, or something like that, and possibly take those learnings and maybe see if we can model that, and then possibly that would be the right approach. Professor, you mentioned that the first gen SpiNNaker system had 1 million processor. The second gen trying to build have put close to 5 million processors. What could be the low hanging fruit? What's been the early use cases, and are there vetted use cases by possibly researchers, neuroscientists? Because you mentioned earlier in the course of the conversation that this could open up huge for implications in space of medicines, neuroscience, neurological disorders. What do you think a neuromorphic computer would be the first few applications of a neuromorphic computer?
Okay, well, just reflect on what you started off by saying then. Of course, there's an important question as to whether we want our machines to be genuinely intelligent, or whether we prefer them to stay as useful automata. I think there's quite an important philosophical question there. General intelligence has advantages and disadvantages. An automata will do what its instructions tell it to do, come sun or rain. An intelligent system may decide it doesn't want to do that, which will make it rather less useful as a production tool. Anyway, to come back to your main question, SpiNNaker 1 was built very much with the objective of contributing to brain science. So the idea was to support, in biological real time, the target was exactly that, but its time is scaled a bit. That's fine. Models of things like the cortex, which we've done, the cerebellum, which we've done to a degree, and try and put those models together so that we can get a bigger picture of what's happening in the biology, and then maybe that will then inform how we build machines going forward. And in the UK, there's actually been some very fruitful research which has taken the SpiNNaker sort of brain-inspired computational model and then applied it to a wide range of computational problems outside neuroscience. So you can use this sort of event-driven computation model, which is the brain characteristic embedded into how SpiNNaker works, And you can use that to compute sort of fluid dynamic flows and heat flows and all sorts of other things. So that's been quite useful. SpiNNaker 2 has been developed to do not only what SpiNNaker 1 can do, but also to be better suited to supporting applications more similar to mainstream AI. So deep neural networks, large language models, and so on. And for that purpose, it has various features added, such as the multiply accumulate accelerator on each processor core, to make it better at that. Where is the low-hanging fruit? Well, I think, if we can demonstrate significant energy reduction running inference on SpiNNaker 2, that will be a significant contribution and commercially quite important. I do think that even the current state of large language models is commercially very useful. We talked about their weaknesses, and what most people see is the kind of general language interface where you can ask it arbitrary questions. But I think those models will become really useful when they're trained on specific areas of knowledge. You could imagine a large language model that had digested all the law books, maybe in the country, because different countries have different legal histories. But and then a lawyer who wanted to find a precedent for a case in court would not have to search through, bookcases full of law books, but would be able to ask an LLM, and the LLM would point them, because it had already absorbed all the information. That's what LLMs are good at. They're good at absorbing vast bodies of information and interpolating. What they're bad at is extrapolating. But there are a lot of areas of work where there are vast knowledge bases that people have to familiarize themselves with. Law is the example I quoted. But you could say the same about, for example, medicine, and many other areas where an LLM that had absorbed the literature from that space would be a very useful tool to somebody working in that area. So those things will come, and neuromorphic systems can certainly work at the inference end. Using them in the training phase is still more problematic because the basic learning mechanism used in large language models, which is error backpropagation, relies on differentiable transfer functions everywhere in the system, and spiking neural networks are notoriously not differentiable. Now, there are approximations that sort of overcome that, but it's still a kind of fairly basic issue. So I think the low-hanging fruit is going to be in those areas. There's also a lot of work in neuromorphics, which is at edge scale rather than data center scale. And again, if you want to run inference on sensor inputs at sub-milliwatt power levels, which is the kind of thing you're interested in there, then neuromorphics has a lot to offer in extremely low energy, small neural networks processing sensory information in ways that at power levels that you can't hope to get to with GPUs.
Right. Professor, you mentioned that there's not many researchers or research labs or companies that are working towards the approach of Neuro AI. Are there any peers that you would like to point out towards who you think are the right approach? Because it's not just neuromorphic computing. There are people who are also trying to build these things called biocomputer, where they're building they're creating these brain organoids. There's companies such as Cortical Labs and Final Sparks. They are actually taking a cell, turning it into a pluripotent stem cell, then an organoid, a brain organoid, and they're building these so-called biocomputers. What are your thoughts on biocomputers, and who you think are the peers who are, who are taking the right approach when it comes to neuromorphic computing?
Well, I think, firstly, I'm not an expert on the biological organoid approach. I'm not up to date with the literature on that, so I don't think I'm qualified to speak. I think it's interesting. But where it will lead, I don't know. In the neuromorphic space, again, there are multiple layers of people working in neuromorphics. There are quite a lot of people whose research is focused at some materials and devices who are producing novel device technologies. MEMRIST is a well-established example, but there are many others where these memory devices have some biology-like characteristics that may make them useful in supporting neuromorphic systems in the future that are much more dense and efficient. Currently, the front-running neuromorphic systems all run on mainstream CMOS process technology, using standard memory and devices. Some are analog, I've mentioned, but a lot are digital. The kind of most visible activists in the neuromorphic system space. I've already mentioned the academic work at Manchester and Brainscales is at Heidelberg in Germany. But there's also industry presence. Intel has the Loihi system, which is a very effective neuromorphic platform and available for academic research. It's a research prototype, so it's not a full product. So you can't currently start a company and say you want to use the Loihi chip, because Intel will not sell it to you on that basis. But if you're an academic group who wants to research an area of neuromorphics, then Loihi is a very effective technology. And Intel have an academic organization called INRC, which is their research, Intel Neuromorphic Research Community, I think it stands for something like that. And they have produced very interesting results, sort of giving a landscape map of which algorithms show significant neuromorphic benefit and which ones are better run on a standard CPU. And of course, neuromorphics will not replace mainstream CPUs. Neuromorphics will always be an accelerator for certain functions on computers, not the general purpose computing platform itself. So there's quite a lot of work being done by that. There's interesting work on neuromorphic sensors, which again is a slightly different space. I mean, the dynamic vision sensor is one of the best known, which is a camera that instead of outputting 50 or 100 frames a second, outputs events when pixels change luminosity by a certain amount up or down. And event cameras show advantages for certain applications. And there are several companies producing those now. Prophecy in Paris. There's a Chinese company that produces lots of event sensors, and I can't remember their name. But Linear Labs in Zurich produces research event cameras. So there's lots of interest, and there are other sensors. There are sort of smell sensors and hearing sensors as well. So neuromorphics is not a single discipline. It's spread vertically from materials devices up to systems, and horizontally through sensors and systems, data center scale systems and edge scale systems. So there are many aspects.
Right, Professor, my last question to you. What would be your advice to young researchers, developers, engineers, right? And because you've got 40 plus years of experience and you've been the pioneer of, creating these processors, which are in 300 billion plus downloads. So your first question, your advice to, the layperson or developers, engineers who are kind of picking up technology. And second, this, during the course of the conversation, you also mentioned, that philosophical question: should we actually build artificial general intelligence or just automatas? Because yes, I think the world is progressing really fast, and I think there is a race of sorts of trying to build these technological stack which will give us some kind of an undue advantage. And I think the nations and the largest companies, they understand that. And it seems like a race to nowhere. So first question, advice to people. Second, your thought on this race of us, the nations and some of the biggest companies trying to build what they call a general purpose machine. Your thoughts?
So I think in terms of advice to young people, I believe I've supervised 36 PhD students to completion in my time in academia. I should say, by the way, I am now retired, so I'm officially an emeritus professor these days. But I think the first thing I would say is to understand what your strengths are and what your interests are, and try and work in an area that you find interesting and stimulating, and then it's easy to work hard and put in the hours required to make progress. I think in terms of where the opportunities lie at the moment, there's clearly a lot of opportunities around AI. I think a particularly important area is the thing I mentioned earlier of applying the current AI to particular areas of knowledge, law, medicine, whatever, developing AI systems that are really useful. AI as a chatbot is very entertaining, but not very important. But AI applied to specific areas of specialist knowledge, I think, could be very important. If you're interested in hardware, if you're a computer engineer like me, then think about where you can contribute to building systems that improve the efficiency, functionality, performance of AI-like applications. I think that's where the space is interesting. On the ethical issues, I'm not too worried about artificial general intelligence at the moment, because I think we're nowhere near understanding how to make it. So it isn't an imminent problem, but I do think we need to ask whether it's something we want to try and develop or not. So if we do develop it, then it will bring with it all sorts of ethical problems that will need to be addressed. If your computer is genuinely intelligent, can you turn it off? That's a very complex area of research in its own right. There are academic researchers who spend their careers on the ethics of those sorts of areas. The big companies, currently the current position with AI is it's so expensive to train a large AI model that only a very few companies can afford to do it. And that puts a great deal of power in the hands of the heads of a very few companies in a manner that's undesirable. I think that will change. There's quite a lot of work going on to try and find ways to democratize AI, so that using it at least at a useful level is much cheaper. And I think that's important, because it's always dangerous to put too much power in too few hands. So we should resist that.
Right. Professor, really, really appreciate you taking time and being part of the podcast. It's been an honor to have you on the podcast. Please keep on doing all the wonderful things that you have done. Wish you great health and happiness always. And really, really appreciate you taking time and being part of the Humble podcast. And to my listeners, if you like what you see in here, then please press the subscribe button. And until next time, see you again. Thank you. Thank you, Professor. Really, really appreciate this. Thank you.